A team of Korean-led international researchers has finally uncovered how charge traps function, a scientific puzzle that has remained unresolved for over 40 years. The finding sheds light on what charge traps are and their crucial role in semiconductor technology. What is a charge trap? Inside a semiconductor device, layers of insulating material and metal are stacked on top of a silicon base. This structure creates pathways that let electrons move. When the voltage is high enough, a path opens up where electric current can flow. When the voltage is too low, the path closes and the current stops. Semiconductors use this difference to read signals. However, if there is even a tiny defect in the insulating layer, that defect can trap electrons for a short time. When electrons take too long to escape or even get stuck, the circuit might incorrectly think that no current is flowing. In essence, a charge trap is a microscopic flaw that disrupts electron flow and can undermine the chip's signal stability. But of course, this doesn't happen because of how people use their devices. It's not a user mistake. Charge traps can often form during the manufacturing process itself, which makes them one of the key factors scientists must learn to control. Nanotechnology and charge traps. The semiconductor industry now stands firmly in the age of nanotechnology. As manufacturing scales shrink, transistors grow ever smaller, and insulating layers ever thinner. But thinner insulation also means electrons can more easily leak or get stuck to microscopic flaws. The smaller the transistor, the greater the effect of charge traps becomes. To fix this, researchers are developing materials that reduce electron leakage. This means that the focus of semiconductor miniaturization has shifted from how small can we make it to how stably can we control the electrons. Using charge traps for technology. Charge traps aren't always bad. If we use their ability to hold electrons in one place, they can actually be turned into a useful tool, specifically a kind of memory semiconductor that stores information. This principle is what makes flash memory, which we use in our everyday lives, work. However, controlling charge traps is not easy. It's hard to predict exactly where and when electrons will get trapped or how many will stay there, so even products made the same way can behave a little differently. Over time, repeating the process of saving and deleting data can also cause slower writing speeds or data loss. That's why, instead of trying to completely remove charge traps, it's necessary to look for ways to use them on purpose. Recent studies are exploring how to control the atomic structure of charge traps so they can be used in machine learning, AI, semiconductors, or ultra-low-power neuromorphic chips that mimic how the human brain works.